Hello, am I audible? पुढे बसा की मला काय तिघात एक चार्ट सुद्धा वापरतो.
Yes, sir.
Okay. Is the screen visible?
Yes, sir.
Yes, sir.
Okay. Yesterday we had seen for this particular part as the condensation evaporation. Basa. And we discussed that minimum 2 heat exchangers required. One has to add the heat, bring it in the two-phase zone, the other to reject the heat, and as such the liquid part could be taken out. So if we try to represent it on the HX diagram, enthalpy concentration diagram, then it looks like this. Let's say your state 1 as shown in the figure is in the subcooled zone. You add the heat, bring it back to the inside the two-phase dome, that is the equilibrium boiling line and equilibrium condensation line. So that is point 2. Then with the help of 3, 2, 4, because that is isotherm, so at point 3 you will get the entire liquid, point 4 you will get the entire vapor. That is okay, but the concentration will be x4, that is not 1. So we are willing to bring it as close as possible to the highest value. So as such, we will not stop at this 4. Then it will reject the heat, bring it back to state 5, which is again inside the two-phase zone. And on 5, I will try to find out the isotherm, which is T5 is equal to T6 equal to T7. So 6 is the liquid state as shown in the schematic also, and 7 is my vapor phase, where now you can observe that 7 falls as x equal to 1. So that is giving me the highest purity. So at such a, if I want to separate the two constituents of the binary mixture, then I will adopt this method of condensation and evaporation. So this will be a series process here. Just I have shown like two parts, what I can say, I cannot call it as cycle, but repetition. So 2 repetitions, 2 times. If you want to achieve the highest possible purity, concentration is one part purity, then I have to add it as a 3 times or 4 times or whatever, n times. So as we can see, there are only, for the simplification purpose, I have shown only 2 heat exchangers, but there will be a series of heat exchangers. The first part is to add the heat, assuming that it is a subcooled liquid. After that, everywhere we will be rejecting the heat. So Q4, 5, similarly, let's say you get 6 and 7, the 7 is not at x equal to 1. Then again heat rejection. So your heat exchanger B and any further heat exchanger will be the heat rejecting part. Only the first one is the heat addition heat exchanger, because your inlet liquid itself is a subcooled one. We have to bring it to the two-phase zone. But otherwise, the vapor phase is always towards the saturated part. So we have to reduce the heat, reject the heat, and bring it inside the two-phase zone. So even if I add further heat exchanger C, it will be always the heat rejection part. Even further heat exchanger D, if required, it will always be a heat rejecting part. Only heat exchanger A is a heat absorbing part, because you want the subcooled liquid to be in the two-phase zone. All other heat exchangers, we are focusing from the vapor point, as can be seen for 4, state 4. So bring it 4 back to 5. You have to reject the heat similarly. If further required, 7 is not at, let's say, x equal to 1. Then whatever, some x7 value there. And I need a heat exchanger C. Then again, it is the saturated vapor. So you have to reject the heat. So maybe 7Q8. As you can see, for 4Q5, there will be another heat exchanger 7Q8, and that is absorption takes place. All other are heat rejection part. Okay, clear? Any doubt? Here we are stopping at 7 because x equal to 1. But if it is not, Then further heat exchanger 7 to somewhere in the two-phase zone. Always we have to go for two-phase zone, separate liquid and vapor. Any doubt to online people?
No, sir.
Okay, so heat exchanger A, where you are adding the heat, so Q1 to 2 will be M1 or whatever, M basically into H2 minus H1. Okay, M1 and M2, they are same because it's only one mass that is coming in and going out. Even for the concentration part also, X1 equal to X2 because you are just adding the heat, why concentration would change. For the separator A, where the liquid and vapor part is getting out, there I have to make the heat balance or energy balance. So M2H2, that is the two-phase part, is equal to M3H3, that is the liquid mass, liquid enthalpy, plus the vapor mass, vapor enthalpy, M4H4. Correct? Now here I know M2 is the total, that is the two-phase part, so liquid plus vapor, M3 plus M4. And for the concentration balance also, since it is just the phase change, so M2X2 is equal to M3X3 plus M4X4. So again, I can draw on the similar lines of the adiabatic heat exchange, adiabatic process, adiabatic mixing process. So on the similar lines, I can find that it is like a inclined line having the same slope, and as such H4 minus H2 divided by X4 minus X2, even if you cross exchange, the slope will be same divided by dx, so as such it falls on the same line. So 2,4 divided by 3,4, that is the total part. 2,4 related to your vapor part, and 2,3 will be your liquid part, and 2,4 will be your liquid part. Okay. This is the same thing which we had done for the adiabatic mixing process. Lever rule and crossway. Yeah. Now the fourth process is the simple throttling. Now we know as far as refrigeration air conditioning is concerned, throttling is isenthalpic expansion. So here the process is having the enthalpy remaining constant. Let's say my inlet condition is 1, exit condition 2, then H1 equal to H2. Now if you observe for the HX chart, enthalpy concentration chart, then during the throttling, it's only the pressure getting reduced, correct? Concentration would not change. Why it would change? So your X1 equal to X2, and being the throttling process, H1 also equal to H2, so you will get a unique point. Correct? The only thing that will change is the pressure. So whatever is the inlet pressure, and there will be some exit pressure whose enthalpy also remains same. So as such, it is a unique point on the HX chart. First point on one particular pressure line, second point on another pressure line, but let's say in a two-phase zone. I will show you on the chart so that it would be better for you to understand. Let's say inlet condition 1, exit condition 2. Now your X1 equal to X2, H1 equal to H2. So your point 1 and 2 will coincide, but your point 2 now is in two-phase. Let's say 1 is your saturated. So naturally after the expansion, your pressure reduces. So your P2 is on the lower side. So point 2 is not on the same, what I can say, temperature, because your pressure is reduced, and it is in two-phase zone, right? So we have to find out that F2G, 1 is equal to 2, that is same, because X1 equal to X2, H1 equal to H2. But your point 1 is corresponding to one particular pressure and temperature. Let's say saturated 1. So some P1 and T1. After the expansion, P1 reduces to P2. Point remains same. Pressure is reduced. So that means the lower pressure line, lower red color line, that we have to find out. Or maybe given, whatever it is. And then accordingly, I need to find out for the T2 in the same logic as F2G. Even if you say F1G, it is one and the same. But I'm not saying it because that is related to state 2, not 1. 1 is the saturated liquid, 2 is the two-phase. Because your pressure is reduced, point remains there only. If the pressure reduced, that means on the lower side, so that is the two-phase part. So this is how the HX diagram can be interpreted. So T1 and T2 naturally will be different. And that is what we want in refrigeration. At the throttling process, H3 is equal to H4, vapor compression, VCC. Pressure is reduced, temperature is reduced. So that is the same thing happening over here. So even though it looks like a unique point on the chart, pressure and temperature are different. Are the online people getting it clear? Offline people got it clear here in front of me.
Yes, sir.
Okay. So now let us deal with it in much more depth. This occurs in majority of the systems because we have to go with the isenthalpic expansion for a refrigeration system. So X1 equal to X2, H1 equal to H2, it forms a unique point for the process of throttling. There is no change. What changes is the pressure, or rather what change are the pressure and the corresponding temperature. Correct? So vaporization may occur during the throttling. That is what we do. In the VCC also, vapor compression also, 0.3 is the saturated liquid, whereas 0.4 is a two-phase inside the dome. Same thing is happening over here. It is inside the dome. Correct? So there is vaporization by trial and error. The example which we had solved yesterday. We have to find out for F2G. So assume any point F on the lower pressure. Okay, construct the equilibrium construction line wala triangle, right angle triangle, find out G and see if F to G falling on the same line. That is our trial and error method. So you have to find out that isotherm, and wherever you get that F point fix, whatever is the temperature T2, that is your final temperature. So pressure reduces, temperature reduces, as same as that in the VCC, vapor compression cycle. Fine. So T2 will be equal to H2 means CPT1 equal to CPT2, T1 equal to T2. So that is possible only for ideal gases. While tackling the numericals, always keep this in mind. If I ask the question for the air refrigeration, you can write down T1 equal to T2. But in air refrigeration, we go for the isentropic expansion, not the isenthalpic one. We use the turbines. Correct? Any doubt online people?
No, sir.
Now this is the example. Try to solve it. Aqua solution leaves the generator at 90 degrees Celsius in just a saturated state at 12 bar. So 12 bar and 90 degrees Celsius. Observe the diagram. 12 bar, 90 degrees Celsius, locate the point. That is as same as H1 equal to H2, X1 equal to X2. And passes through a throttle device. The pressure after the throttling is 4 bar. So I have to trace the 4 bar line. Assume some F. Trial and error. Find out G with respect to 4 bar now, not 12 bar. And find out F to G. Wherever it matches, that is your temperature. I got the value as 60 degrees Celsius. What is asked? Obtain the concentration of the liquid and vapor before and after the throttling. So concentration before, that is very common because X1 equal to X2, that doesn't change. Okay. And for after the throttling, that means liquid concentration and the vapor concentration. So F or XF and XG. You need to find out, cross check the answers. Everything is in front of you. So try to solve it and cross check. तीन लोकांना दोन चार आणखी कोणी आलं तर म्हणून ठेवला कोणी गेलं वाटत 12 बार म्हणजे किती झालं 1200 kPa. बरोबर 1200 kPa आणि 90 डिग्री सेल्सिअस. इंटरसेक्शन पॉइंट काय? सापडला? कॉन्सन्ट्रेशन चेक करा. 0.39. Now that is the same point as 2. 1 is equal to 2. But now the pressure is different. So trace the line for 4 bar. That is 400 kPa. And then assume for F, find out G and check for F to G. Online people, are you getting X1? 0.3839, whatever it is.
Yes, sir. Sir, getting 0.4.
Okay. 38394, whatever it is. Now your 0.1 is equal to 2. Only thing change is the pressure and corresponding temperature, of course. So now you have to trace the line for 4 bar, that is 400 kPa. Then assume any point F. Now I have given the answer, you can cross check 60 degrees and 4 bar. Find out intersection. Construct the equilibrium construction line wala right angle triangle. As you know the answer directly, 60 degrees Celsius, I have shown it. And cross check the right angle triangle and F to G. Both should get satisfied. And then read your XF and XG. काल कर्नल सरांनी लेक्चर हे केलं का पोस्टपोन केलं का मला ते म्हणाले हां कुठला तरी फ्री स्लॉट होता हां 0.97 लिक्विड स्टेटचं बघा online people getting X liquid and X vapor, XF and XG. I got 0.34, you make it 0.33 or 35, whatever. तुमचं किती आलं? 33.
3.2 येतं.
3.2. कमी आलं. Vapor part?
9.6.
9.6 is okay. ठीक आहे बघूया. Okay, are you getting? Should I move ahead? Offline people got it.
Yes, sir.
Online also got it. Now, as I said yesterday, the rectification of the binary mixture. So the same logic which we discussed yesterday, one heat exchanger to add the heat, bring the state in the inside the dome, that is the two-phase mixture, then first liquid separation, first vapor separation, then reject the heat from the vapor part. So again two-phase, again liquid separation, vapor separation, and etc., etc. But that is a tedious process in a sense that it will require number of heat exchangers. Correct? This is the process which we had seen, condensation and evaporation process, rather the blend of that. So this heat exchanger A, we call it as a generator because it adds the heat and generates the two-phase mixture for the separation. Okay, so this heat exchanger A, we call it as a generator. This is a very standard terminology which we'll be using further everywhere. And the one which is rejecting the heat, we call it as a deflagmator. Okay, since it is the separating deflagmator. Fine. The combination of those, one generator and minimum one deflagmator. Generator will be always one, single. Deflagmator may be in series. So combination of this generator and minimum one deflagmator ultimately gives me the vapor of some high purity value. You go on adding the number of heat exchangers, you will get the purity at the highest. Correct? At the exit of the deflagmator. So what we have seen is state 5. Correct? And then 6 is liquid, 7 is vapor. So at the heat rejection, I get state 5 as the two-phase part, out of which 6 is liquid taken and 7 is of my interest. Now here, for the sake of simplicity, I have shown 7 directly at x equal to 1. But if it is not, then you can add heat exchanger C, which will be another deflagmator, and then you may get 0.10 over there. So as such, you move towards the right-hand side as the vapor of the highest purity. Correct? This is what we had discussed. However, this is inadequate for the separation of the binary mixture. Inadequate in the sense, very, very lengthy process, very, very bulky system it would be. Correct? Because you go on adding the number of heat exchangers and then liquid separation, vapor separation, then again heat addition, etc., etc. This is a simple technique. We are actually doing the same, but in a very concise manner. So how we achieve this? Let us study that. So what is something called as the rectifying column? Between the generator, that means the first heat exchanger, and the deflagmator, which is the last heat exchanger in this case. So there will be only one generator, one deflagmator, and the entire separation would take place in between this. So no need to add on heat exchangers. It's a simple column. Why we call it as a rectifying column, that I will explain in the next slide. Okay. So it will be a vertical column. At the bottom there will be generator. You add the heat. Okay. Vapor part, because of the addition of the heat, it starts boiling. Vapor part goes in the upward direction. There you reject the heat as the deflagmator. So naturally, after rejection of the heat, the condensate starts falling down under the gravity effect. So liquid falling down, vapor going in the upward direction, and in between is this rectifying column. So let us see how it works. So this is something called as the rectifying column. Here V represents the vapor phase, L represents the liquid phase. So what you do with the heating medium in the generator, that will add the heat. So the liquid starts boiling. Vapor goes in the upward direction. Okay. At the top, there is a deflagmator, cooling water. So there will be condensation. The liquid part, condensate, starts falling down. Now, in between this, there are number of plates. These plates are the perforated plates. And what happens over there is the vapor part, in bracket somewhat higher temperature, and liquid part, in bracket somewhat lower temperature. They also exchange the heat. Since there is delta T, it will exchange the heat. So even if there are any traces of the liquid part in the vapor phase, that will get condensed out. Heat exchange चल रहा है दोनों के बीच में. And that liquid part also falls down. And even if there are certain traces of the vapor part in the liquid phase, that will absorb that heat and again go in the upward direction. So instead of adding the number of heat exchangers in the horizontal manner, I'm adding it in the vertical manner. And I'm making the vapor and the liquid phases to continuously have the heat interaction. heat transfer. Ideally, what is expected? Entire vapor, upper side, entire liquid, lower side. Of course, that is not going to happen in one single, let's call it as now cycle. It's not going to happen in one single cycle. So what we do, we continuously put it on heat added and the heat rejected. So there will be continuous flow of vapor and liquid. Boiling on the left hand side, let's say V, and condensation, that is right hand side L. Is continuously going on. And even if there are the traces, then that also will get separated out. So what is the meaning of removing the traces? Increasing the purity. When I remove the traces of the other component, that means I am increasing the purity. So it will be entirely vapor of, let's say, component B and entire liquid of component A. Even if there are some traces of component A, liquid, in vapor phase, heat transfer in between is continuously going on at every plate. That is why those are the perforated plates, and those are stacked in the alternate manner, so that vapor will flow in any random manner because it is free to flow the way it wants, and the liquid starts dripping down through the perforated plate because it is at higher density, obviously. We do not put it as a cup, वरना वो उधर ही रहेगा. I want the liquid at the bottom, so we put it as a perforated one. So under the higher density and gravity, both effect cumulatively, liquid will fall down. Vapor at the lower density go at the top. So I will get component B pure vapor as state 3 and component A pure liquid as state 2. And why I have written over here as weak liquid? Because it is separated now. Your inlet condition 1, I have written strong liquid because it is A plus B. Subcooled. So now after the separation, I will get only component A liquid. So I call it as weak liquid. And component B vapor, that is state 3 at the top. Okay, so instead of wasting the space in the horizontal manner by adding different heat exchangers, I'm adding it in the vertical sense. So that way I can save the space and I'm getting the effect of the density difference. Vapor will go in the upward direction, liquid will fall in the downward direction. Plus gravity. So wastage of space reduced, material reduced. I need not have different heat exchangers. It's simple plates. So material wastage reduced, space reduced, time reduced, cleaning, maintenance, overhauling, सब कुछ reduced. So this is called as the rectification column because you are rectifying the two phases, liquid of component A, vapor of component B. Fine. So this is why we call it as a rectifying column. Pieces of the liquid get condensed out. Correct? Is the connection there or gone?
Yes, sir.
Can you see the slide?
Yes.
And the liquid L that will start dropping down, and even if there are some traces of component B vapor, then that will get condensed, evaporated, move in the upward direction. So I'm just making the use of a simple natural physical phenomenon, that is density difference. जो अगर मैं हॉरिजॉन्टल में लगाता तो नहीं मिलता. I have to apply a completely different heat exchanger, entirely new heat exchanger. Here the heat exchanger is a direct contact as the number of plates, and since it is a direct contact heat exchanger, effectiveness is the highest. There is no loss as such, correct? And as I had mentioned earlier, the vapor phase progressively in the higher concentration in upward direction, and the liquid that is progressively weaker. So weaker means only one component. Okay. I'm saying component A and B. From that perspective, if you can write like progressively higher concentration for component A, correct? Yes. Vapor concentration for B higher, liquid concentration of A higher, correct? Fine. So this is how you separate the two phases, or sorry, two components. One in liquid phase, the other in vapor phase. Fine. Any doubt to online people?
No, sir.
Now here there is a slight change, and what I have done is the strong liquid inlet condition is slightly on the upper side. Why? Logic again same. Same heat transfer. Liquid falls down, vapor goes up. So instead of making the entry at the bottom, put it at somewhere middle section. So again vapor and liquid heat exchange, direct contact heat exchanger, more effective. Simple logic. Instead of making the entry at the bottom and then boiling, anyways vapor phase is at the higher temperature. So add the liquid itself at the, let's say, some center point, so that the incoming liquid itself starts heating, getting heated there only. Not at the first part, of course, first cycle, second, third, fourth. When the QG part, generator heat, comes into picture and the separation would start, the incoming next lot of the subcooled liquid that gets separated, two parts, liquid and vapor, at the entry itself. So my QG reduces. If I put the entry at the bottom, then QG would be more because I have to supply that much amount of it. But now, let's say, 10 ml. 10 ml liquid comes in, you add QG, thoda sa heat, and the separation starts. Now the next lot of 10 ml which is coming as the strong liquid at the somewhere middle section, that is at room temperature. Vapor phase is at higher temperature. So there itself heat transfer starts. So for the separation of the next lot of 10 ml strong liquid, the QG requirement is reduced. What I want? Inlet reduced, COP higher. Okay, so I just made a simple change as the inlet condition not at the bottom, but at somewhere on the higher side, so that ultimately my QG reduces. QG is the input I have to reduce. Correct? So this part has a special name that is called as the double rectifying column. Earlier what we have seen is single rectifying. Now your inlet itself is, let's say, at center. It's not exactly center, somewhere in between. So the upper part, we call it as the exhausting column, and the simple rectifying column as it is over here. Okay. So the vapor boiled off in the generator goes in the upward direction through the exhausting column, ye, niche wala, till purified to the value of the state 3' at the entry itself. I will get the benefit. More purity. Because already certain part getting separated over here. So further part is like an added advantage. So more purity. Correct? Further concentration in our regular upper wala part, rectifying column. So exhausting column increases the purity up to certain level, rectifying column remaining part. But because of this change, simple change, my QG reduces. I need not supply the entire heat for the 10 ml. Because 10 ml means 10 ml at some particular temperature. My inlet temperature now itself is increased. So separation starts immediately. Correct? So your final value, final state 3. Let's say certain part, certain percentage is already achieved, 3 dash. Somewhere in between. And then further rectifying column. So load on the rectifying column reduces. Correct? So the strong liquid solution state 1, let's say subcooled liquid, correct, gets mixed with the liquid living in the upper column. And of course vapor also. That is why there is a heat transfer. So liquid falling down, isme ye liquid. That is something which I want, desired effect, liquid separation. And the liquid getting mixed with the vapor in the upward direction, vaporization starts. So liquid side condensation in bracket down and vapor side evaporation in bracket upward direction. Okay, so my QG, that is the inlet value reduces, and that is what I want to reduce the, increase the CO2. So this is the animation for the actual vapor absorption system. Can the online people see? Because here I can see it clearly.
Yes.
So now you can see over there, the condenser, the throttle and the evaporator remain same. What we have exchanged is the compressor. Okay. Now there is a heat source. That is our generator. Okay. Look at the bottom side, it is an absorber. So refrigerant red color getting absorbed and the absorbent blue color. The strong solution is pumped. Then you add the heat. That is your generator. At the top, that is the second stage generator jo bhi likha hua hai. That is basically the deflagrator, where the separation is taking place. And the liquid part of the adsorbent is coming down, blue color. Vapor part in bracket refrigerant, red color, that is going out. So second stage generator is basically the deflagrator, and in between the generator and the deflagrator is my rectifying column with those plates. Okay. So that is why I have selected this animation, because the arrow diagram and everything is very clearly self-explanatory. Okay. So in the absorber part, the absorbent will absorb the refrigerant, make a binary mixture, which is, let's say, subcooled. It goes via the pump. The pump will throw it at the generator part. You add the heat. In the deflagrator, you reject the heat. So there will be that final separation. Vapor part in bracket refrigerant, red color. Liquid part in bracket absorbent, blue color. Absorbent will come down. We call it as weak solution. After the absorption, strong solution. Okay. Weak means only absorbent. Strong means refrigerant plus absorption. Okay. So through the pump, it is always a strong solution. And after the deflagrator, whatever falling down, blue color, that is a weak solution. That is what's shown over there. Are the online people clear with the diagram?
Yes.
Any doubt? Condenser, throttle, evaporator, everything same. That is pertaining to only refrigerant, so there is no change. What is change or exchange rather is the compressor with a absorbent, or rather I would say absorber section, generator and deflagrator, of course, along with the pump. And now you can realize that the compressor work, which is related to the air part, no, not air, I should say, vapor part, gaseous part, there the volumetric changes are very large. So PDV work is large. For the pump, it is the liquid part. PDV is very small. We consider liquid as a incompressible. So pump work is very, very negligible because you are dealing with the liquid part. In the VCC, the compressor is for the vapor part. And that is what, if you could recollect, I have shown in the first slide, that the PDV work for the compressor is much larger. Here we reduce the PDV work because the DV basically itself is very, very small. Why? Being the liquid. Pump work is very small as compared to the compressor work. So your inlet reduces, COP increases. And if you further recollect that I have rather shown over there, I have discussed over there about the thermal energy inlet, which is required for the absorber, for the separation part, no? Absorber and deflector. So the thermal energy inlet is the only main part as far as the performance is concerned. So that is why this particular system is very, very appreciated, where you are having free thermal energy. For example, solar energy, wind energy, biomass energy. Vapor absorption rate. Hello, am I audible?
We're not audible. Yes, now you're audible.
हाँ,
Yes,
I
sir.
got a call. बैंक वाले कॉल करते हैं ना, लोन चाहिए क्या? So even if there is no electricity or severe load shedding, then you can use such kind of refrigeration system. Your pump work is very, very small. You can use a hand pump also. गांव में देखा है ना ये hand pump water. You move the
sir.
piston up and down. हाँ, बस खत्म. Volumetric changes are very small, so manual work is more than enough. You need not go for the electrical work. Simple mechanical work is sufficient. So even though you do not have the electricity, or you do not, or you have a very severe load shedding of 8 hours or something like that, and you want the refrigeration effect, you use the vapor absorption system. So this is how it works. Hello.
Yes, sir.
Any doubt to anyone?
No, sir.
Okay. So now let us go for the thermodynamic analysis. This is what is the system, correct? Condenser, throttle, and evaporator as they are. So QC heat rejected, QE heat absorbed, condenser and evaporator, throttle, and the extra part or the substitute part is the compressor, which I have replaced with the absorber, generator, and even some intermediate heat exchanger. Okay, so in the generator, my input is the QG. And in the absorber, you are rejecting that heat. You want to make the mixture, na binary mixture, so you have to reject the heat. And the pump work, WP. So I have 4 energy components, QC, QE as they are earlier, condenser and evaporator. As far as the vapor absorption system, generator, heat input, so QG, in the absorber, heat rejected. Correct? and then in very nominal work, that is the pump work. Okay, so I will try to put it in the energy balance. For that, my assumption is that the absorbent does not vaporize. Obviously, अगर absorbent ही खुद vaporize होके condenser में चला गया तो क्या होगा? Entire system गई 12 के भाव में. So we want a liquid absorbent always and vapor refrigerant. Correct? So that is our basic assumption. Then, state 1. Now look at the state 1. That means at the inlet to the pump. Correct? The vapor leaving the evaporator, matlab refrigerant of course, plus the weak liquid solution. Weak means not absorbed. Simple absorbent. Correct? Now that there will be the absorption process. Then the removal of the heat. So your refrigerant vapor will be absorbed by the weak solution. QA, removal of heat. And what I will get as the inlet to the pump is the strong solution. Strong means absorbent plus refrigerant. Correct? Now the pressure of the liquid solution will be increased by the pump, correct? Pump inlet pressure some 1 bar, outlet pressure maybe 5 bar, 10 bar, whatever it is. But the corresponding PDV is very less because you are compressing the liquid, rather trying to compress. Now I reach to the generator pressure, which is at the high value. In short, basically condenser pressure. Generator pressure means condenser pressure. Correct? Then the heat addition. Why? Because now I want separation, deflagmation. So refrigerant vapor will be driven out of the liquid solution when you add the heat, deflagmator, liquid vapor separation. Liquid absorbent falls down. Vapor refrigerant, further condenser part. Correct? So it's only the heat transfer, pressure remains same. So in the heat exchanger, the liquid solution circuit between the generator and the absorbent, इसके बीच में the blue color, that is the same logic. The weak solution which is coming in and the vapor part, no, not vapor part, two-phase part in the at the outlet of the pump. Naturally, temperature differences because there you are adding the heat. So your weak solution is at higher temperature and this pump solution is at lower temperature. So heat transfer in the way, in the process itself. No separate heat to be supplied. So with this what I achieved, QG reduced. Correct? Weak solution temperature is higher. Strong solution temperature is lower. जाते जाते बीच में heat transfer. So that the QG to be supplied is reduced. And that is what I want. Inlet minimum, outlet maximum. Correct? So generator plus condenser, that is my high pressure side. ऊपर वाला. And evaporator and absorber, that is my low pressure side. And the pressure differential is created with the help of a pump which deals with the liquid. So my WP is also less. Because of the heat exchanger in between, my QG is also reduced. I'm trying to reduce every input parameter. Maximize the evaporator load, refrigeration effect. So if I try to summarize in the simple way, then generator at the temperature Tg and gives the heat Qg to the absorption system. Correct? You have to supply that heat. Then pump also WP, that is the input to the system. Correct? Refrigeration space TE, that is also absorbed. Correct? And everything is rejected to the environment. Absorber is also rejecting the heat to the environment. Condenser at the top, that is also rejecting the heat to the environment. So instead of that two things, absorber and condenser, I have written Q naught. Q naught is basically QA absorber plus QC condenser. Okay. Energy transfer to and from the vapor absorption system, fluid. So generator, heating medium, QG. Correct. Pump, that is also work addition, WP. We try to reduce WP. How? Liquid. We try to reduce QG. How? Internal heat transfer, heat exchanger. And the substance to be cool, that is your refrigeration effect, which you want to maximize, QE, evaporator. And everything getting what is rejected is this Q naught. There are two parts as we discussed. One is the absorber heat rejection, the other is the condenser heat rejection. And both are rejecting to the atmosphere, so I can write down Q naught. And T naught, of course. Temperature is T naught, environmental temperature. And whatever cumulative QA and QC, that is the total heat rejected. The heat rejection से मुझे कोई लेना देना नहीं. I am interested in QE. That is my desired refrigeration effect. And WP and QG, because that is my input. Correct? So now we will try to put it in the thermodynamic formula. Q naught, environmental part is QA plus QC. A is absorber, C is condenser. Correct? Then we apply the first law. What is the total energy balance? Total rejected part Q naught, which is basically Q and QC, is equal to QG generator plus QE evaporator plus the WP. Total energy balance, work and heat. Now I will make certain assumptions because this is a theoretical analysis. So the generator, whatever heating medium, its temperature is maintained at TG. Whatever, let's say heat supply, let's say kerosene or some gas you are burning, 300 degrees Celsius, we assume it to be constant. Okay, valid assumption, nothing wrong in that. Refrigeration substance temperature TE, that is also we assume to be constant. I want the refrigeration effect at minus 10 degrees Celsius, constant. Okay, and the environmental temperature constant. This is also valid because we take it as a thermal energy reservoir. MCP is maximum, delta T is 0. Correct? Second law, chapter 4, same 3. So all these are constants. That is what is our assumption, and these are very much valid assumptions. Nothing wrong in that. Right? Now I will put it as a closed system because no mass coming in, no mass going out, everything is moving in a cyclic manner. So a closed system. When the steady state operation is achieved, that means all the temperatures, everything getting stable, then I can write down delta S is 0. It's a cyclic part. Correct? Now I will put this entropy as Q by T. So delta S at the generator will be the same Q and T, QG and TG. And since it is the heat absorbed, I put it as minus sign. Where that is undesired effect. Correct? Substance to be cooled. There also it is absorbing the heat. So minus QE by TG. Evaporator, no? Then absorber. Here we are rejecting the heat. So plus Q naught by T naught. Right? I will put it in the first law part. Oh, sorry, second law part. Total entropy change is equal to the sum of the individual entropy changes, and being the irreversible one, it is equal to greater than 0. If by chance, luckily, you prove it to be a reversible one, then equal to 0. So you put it as the formulae for the entropy or other entropy change. So minus QG by TG minus QE by TE plus Q naught by T naught. Q naught is absorber plus condenser. Okay. Now I will try to put it as the theoretical limit. So I will write down Qg into Tg minus T naught by Tg. Just the mathematical cross multiplication. इसको 0 पकड़ लो. Equal to 0 पकड़ लो, for example. तो Qg by Tg, Qv by Te and Q naught by T naught. Trying to rearrange. Okay, so Qg part and Qe part. Where it would be To minus Te divided by Te. And Wp, work required for the pump, is kept separate. Because that is a work interaction. All other remaining are the heat interactions. Fine. And now you can observe that if I suppress this Wp, compressor pump, pump work is very, very small. So if I put it at 0, then what I get is Qg into this bracket on the left hand side and Qe and the other bracket on the other side. So while getting transferred over there, it would be the reciprocal, Te divided by T naught by Te. Correct? And then I will try to find out the COP expression. What is my COP? Refrigeration effect QE, evaporator, divided by the input Qg. And then if you rearrange the terms of the temperatures, because QE and QG are associated with some temperature brackets. If you try to put them as the ratio, then what you will get is this Te into bracket, Tg into bracket. And now you can observe that Tg minus T naught divided by Tg. One term. And Te divided by T naught minus Te. Another term. One is a Carnot engine efficiency. The second is a Carnot refrigerator COP. One is delta T by T. The other is T by delta T. Correct? So if I try to put it in proper way, let's say I assume a reversible cycle, so that less than wala part there, and I will say equal to. Reversible means irreversibility is gone, na? Less than, greater than, and equal to. Then I will rearrange this as I just said verbally, and I will say Te divided by T naught minus Te, one part. And delta T, that means Tg minus T naught divided by Tg. That is another part. So I will say that the maximum COP of the vapor absorption system that you can get is the product of one refrigeration COP and one engine efficiency. The refrigeration COP is between Te and T naught. Correct? T low divided by delta T. And the Carnot engine between Tg and T naught. Because over there, delta T divided by T high. Right? Tg is T high, na? Generation. So this is the unique example in the entire thermodynamics applications, where COP, performance of one system, is expressed in terms of performance product of other two systems. And those other two systems are the ideal. Because one is Carnot engine, the other is Carnot refrigerator. You need not worry about whether it is vapor compression or vapor absorption or anything. Air refrigeration. I need not worry anything about it. It's just the Carnot. So the moment you come to know about the temperatures, you can find out the COP, correct? Environmental temperature, generator temperature, evaporator temperature, pump work anyways neglected. The moment you get these three temperatures, Te, T naught and Tg, evaporator, generator and environment. You can calculate the COP, and that is the maximum one, theoretical. Because Carnot is theoretical. Okay. So this is the beauty of vapor absorption system. The COP of one system is expressed in terms of performance indicators of the other systems, and that too ideal. Because one is COP, that means refrigerator, the other is efficiency, so that means engine. Okay. So you can optimize for the given T naught, because T naught is something which is not in your hand. Environmental temperature can be anything. So for the given T naught, you want to increase the COP, increase TG, correct? And reduce TE. And now you will observe that here is a contradictory part. In VCC, we used to say that lower temperature should be as high as possible and higher temperature should be as low as possible. And here we are saying higher temperature should be as high as possible and lower temperature should be as low as possible. Exactly reverse of VCC. Fine. So this is how vapor absorption system works. In practice, naturally, hundreds of irreversibilities are there. So the practical COP will be much lower than the theoretical one. So always remember as a thumb rule that practical COP for any vapor absorption system generally falls as 0.5 to 0.7, not more than that. If while calculating in your MST, EST, whatever it is, if you find out the COP as 2.3, then cross-check the answer. Okay, 0.5, 0.7, not more than that. Fine. Any doubt? How much time? Arey, time over. Chalo. Any doubt to anyone?
No, sir.
Online class, very good. This is the aqua ammonia vapor absorption system. What you can observe is the evaporator same, absorber same, condenser same. The rectifying column I have shown in full depth. And two more heat exchangers added. One, as we said, for reducing the TG. And the same logic is done after the evaporator also. Because I want over here complete vapor at the exit of the evaporator. Refrigerant must be vapor phase. तो जाते जाते उसको और गर्म करो, होगा कुछ लिक्विड तो वो भी वेपर हो जाएगा. Right? So all these are the practical modifications so as to confirm about the liquid phase, vapor phase, reducing the heat input and etc. etc. Okay. Oldest method of refrigeration. The name itself is aqua ammonia. Here the refrigerant is ammonia. The absorbent is water. Okay, aqua. Now water, volatile in the sense it may go into steam phase. So that is a problem because steam should not go in the condenser. If it gets condensed and further after the expansion, it will form ice and the entire evaporator will get choked down, rusted. So there should be some care to be taken. So rectify the generator vapor, supply more and more heat so that only ammonia will go over there and this, what you call, water, H2O, that will come down. No H2O should go to the condenser. That is the care to be taken. Correct? So we have the double rectification column plus the deflagmator plus some kind of heat exchanger where if at all any water traces would be there, water in the then to further part. Correct? If you consider, instead of aqua ammonia, if you consider the LiBrH2, then there is an advantage to us. Here the refrigerant is water and the absorbent is LiBr. So I need to play only between the liquid vapor, liquid water and steam. Okay, so that is a LiBr is non-volatile. It always remains in liquid phase. Ammonia or water में ये problem था. Correct? So here there is no such problem. Okay. So no rectification column. LIB are always in liquid phase. कुछ भी करो उसको, उसका boiling point बहुत high. So I will play only in liquid H2O and steam. Rectification column gets itself rectified. No need. Correct. So that is the biggest advantage. Simple. No rectification column, so bulky नहीं है. Cost wise smaller amount because no investment for rectification column. COP is higher. Aqua ammonia इससे better है. LIBR. The only limitation is that since you are using the refrigerant as water, you cannot go to ice. How it will flow in evaporator. So there is only limitation as the temperature limits. You cannot go below 4 degrees Celsius. Anomalous behavior of water. No. So if your refrigeration requirement is, let's say, 8 degrees Celsius, 10 degrees Celsius, then you can use it. You cannot use it certainly for -5, na? Ice ho jayega. Okay? Fine. So that is the only problem, limitation. Fine. This is the schematic for the LIBR system. Same logic, condenser, evaporator, strong solution, absorber, and generator, weak solution. Mirror image type में दिखा हुआ. This is the comparison part for the vapor compression versus vapor absorption. Very, very logical. You can read it. Nothing to explain as such, because everything is explained in all the previous lectures. So you can read it afterwards. So here we end up with this particular chapter. Okay. Any doubt to anyone? Online class?
No, sir.
Good. So should I end the meet? Next lecture is ready. Professor is there.
Yes, sir.
Okay. Chalo, fine. Thank you.